Welcome to our virtual booth and thank you for joining us. In simulation use case 3, we tested components of different sensor technologies in an open loop simulation environment. In this presentation, I'm going to show you the camera-based tracking. Here we can see the 3 simulation use cases mapped at different stages of the V model. The component testing is located at the bottom. Focus of our use case was the verification of sensor functions. Therefore, we wanted to integrate representative elements of a video camera sensor system. In the following, the elements we are looking at are different sensor functions. For integration, we use standard interfaces in an open loop simulation chain. The D-space toolchain was used to provide a high-definition environment for the camera rendering. Now come to the preparation of the simulated scenario. For our simulation use case, we used an open drive and open scenario import of a 4-way junction with an occlusion of a crossing pedestrian. The situation is shown here. The truck turns before the ego vehicle reaches the junction, and the pedestrian, illustrated with a green arrow, is crossing the street during the truck's turning process. And therefore the truck occludes the pedestrian. The ego vehicle recognizes the pedestrian in a late stage of its turning process. We'll now have a look at the toolchain and the integration of the system under test. And here we can see the D-space toolchain. On the left, we have the automotive simulation models that provide information about the vehicle dynamics and the traffic environment. And the D-space tool Aurelion supplies the system under test with ground truth information, for example, RGB, optical flow, or depth. And in set level, we developed new and enhanced already existing open simulation interface sensor view structures, which were also implemented in the D-space toolchain. The simulation itself was performed on the simulation platform VEOS, which you can see here. And the camera model itself was developed by Bosch and packed as a functional mock-up unit. The communication interface between tool and system under test was the ASAM standard open simulation interface. The visual output calculated and generated by the system under test was compared to the ground truth provided by Aurelion and then visually evaluated. We'll now have a closer look at the sensor simulation tool Aurelion in a small live demo. And first, we had to prepare the tool to fit the needs of the system under test. And here we can define the used sensor technology, in our use case, a camera. And we can then configure things such as the resolution, the field of view, and the sensor types, and where to place. And then we can place them where desired. And what we can choose what image data to provide in detail. Here we can see we select vehicle, we can select also a truck or a normal as this one, and we use the already configured camera sensor and place it where desired. Place it by drag and drop, and the exact position is further adjusted. This mounting position is an important information for later coordinate transformations, and it is provided in the OSI structure. The simulation is now prepared, and this configuration can be used in every conceivable scenario. Now we will have a closer look at 3 of the tested sensor components in our execution and evaluation part. And I will hand over to my colleague, Dirk Rappelger. I'm sorry, I just have to start the presentation again. Okay, you can start from here.
Yeah. Hello, everybody. Let me start the execution and evaluation of the optical sensor, the camera sensor we developed in the Z-level project. To start it. We choose to focus on three main algorithms of the camera sensor for the tracking task. The first of all is the optical flow. This algorithm cannot be tested by human-labeled ground truth data because optical flow describes the movement of a pixel, or better, the world movement of a small patch and its projection through the optical lens systems onto the sensor image plane. This algorithm is obviously essentially important for camera-based tracking due to the fact reliable testing is important also in TUC. We implement the open loop testing and present the result of the chain. As you can see here in this still image, we get the RGB image from the environment. As an overlay, we calculated optical flow, and in the upper left part, the ground truth data. It is common to encode the optical flow in rainbow colors. And of course, the goal of the calculation is to estimate a dense flow field. It means every pixel of the input gets a valid optical flow. But for tracking reason, it is obviously to get a reliable sensor and not a bunch of random walk. Therefore, you can see some holes. It is better to deliver holes as wrong optical flow. When we show the film, you can see the good quality of the calculated optical flow compared to the ground truth delivered by the environment. Haben wir es wieder gemacht. Start it again. Sorry, I'm sorry for the test. I completely lost. And now start again. The second fundamental algorithm we present is the depth estimation. Now we the movement, and for camera-based object detection, it is necessary also to know where an object is. Where an object is, we choose stereo information that is well known from our human behavior. We have two eyes, and so we can estimate the depth of the environment in front of us. The images are delivered also by the well-known OSI image standard. And here we can see both image from the left and the right camera. At the first glance, the images are quite the same, but also when you have in remembering your own visual context, the left eye sees something different of the right eye, and this difference is called a displacement or disparity, and that is the measurement we did in computer vision. On the bottom of these images, the ground truth is displayed, and here it's a common visualization of the depth from the near plane up to the infinity, from hot red color into cold blue color. And if we start it correctly, can see at the first overlay window as the same reason for optical flow. It's better to get an impression of correct depth values instead of a lot of bunch of erroneous values. And here you can see the mask in blue as overlay. Here the values of our depth estimation can be calculated seriously. And this performance indicator can be seen on the upper overlay window. Here it is visualized the difference between ground truth and estimated depth. And it is visualized, the more blue, the more deviation of the depth estimation and ground truth can be detected. And here you see in the infinity, or more or less in the infinity, the colors blue appears. Now we can estimate the movement of an object. We know the depth of the object, but we didn't know what kind of object we saw. And this is the last task. We choose to implement prototypically object detection itself. The object detection itself is more or less the most complicated version of computer algorithm because it is it has so many parameters to implement. And here the ground truth generation with an environment like the D-space toolchain is essentially for further implementation and evaluation. We saw here, or we see here in the image, the ground truth RGB data. And of course, what you see is the rectangles, the bounding boxes around the object that we can detect. We can supply from the environment. Here you see we have some bounding boxes around the lorry, and we see the bounding boxes around the car standing right to the ego lane. Here you see, unfortunately, some error in our detection, and it's not that we just want, but with the testing toolchain we implemented prototypically in the set level project. We laid the foundation for the work, and it is very necessary to invest more work into this topics of testing and validation of our systems. Thanks for your attention, and now we are happily to get questions. Many thanks.